Welcome, everyone, to another CO2 Monday in the Refrigeration Mentor podcast. I'm your host, Trevor Matthews. And once again, I want to thank you for taking the time each week to come to these CO2 sessions and listen to them on the Refrigeration Mentor podcast, because this is how you grow your knowledge. You take your time, you learn a little bit each week, and over a year, that's a lot of knowledge. And this is how I'm learning. I'm bringing experts on here, just like Daniel. Today, we're going to be diving into some awesome CO2 content on CO2 heat pumps, because he is the expert at it and he's been doing it for well over 10 years. And I'm super excited to get into this conversation because I'm still learning about CO2 heat pumps. I dabbled here and there with CO2 or with heat pumps before I got into CO2, but nothing like I am learning now. And what I'm excited about it, because this is a growing field. Heat pumps is over the last 5, 6, 10 years has been growing immensely, but now it's growing even more with these net zero goals, carbon reduction, electrification, getting rid of these natural gas systems, these big boilers, something that causes a lot of, puts a big carbon footprint on our planet. So CO2 heat pumps is something that is growing very fast, and I'm super excited, like always, to learn a little bit. Daniel, how you doing, brother?
I'm very well, thanks. Very well. It's a bank holiday here in Britain, so
Oh, thank you for doing this.
yeah. I hadn't realised when I said yeah, but it doesn't. Yeah, it's great. I've had a good day off, but yeah, it's
Now I'm putting you to work. Now I'm putting you to work.
yeah. But
Why
no
don't
problem.
you why don't you give a little introduction for those who don't know you, about you and a little bit about your company and what you guys do?
Yeah, so we, as Trevor explained, we've been working with CO2 now for 15 years, I think, well, 16 actually this year, 2007. I went over to the Danish Technology Institute in 2007. There was only about 6 or 7 Brits that went over on a trip that was organised, and it was right at the infancy of CO2 adaptation for refrigeration. And, we quickly understood that it was going to be the technology of the future for refrigeration, particularly at the time. And with the HFC legislation getting tighter and tighter and tighter, we always knew it was going to, explode to be the mainstream refrigeration technology in certain sectors, if not the majority of sectors in refrigeration. So we got really good as consultants with CO2 and adapting, working with companies like Carrier and Advancer and Green and Cool and all the early starters with CO2 technology. And then I've always had a passion for getting my hands dirty and building stuff, growing up on a farm. So we decided to become a system manufacturer in about 2017, and things have gone very well since then. We're concentrating predominantly on industrial refrigeration with carbon dioxide as a refrigerant. We're seeing more and more inquiries just recently coming in for heat recovery off CO2 plant, which is effectively creating a heat pump out of a refrigeration system. So we've got systems that are actually refrigeration systems, but are a heat pump at the same time. And obviously now with the net zero agenda, there's a big focus coming into heat pumps. We're focusing more on large scale heat pumps with carbon dioxide as a refrigerant. So there's a twofold emphasis on what we do. One of them is obviously the net zero and everybody wanting to go away from burning natural gas, particularly in Europe and the UK at the moment. And then obviously the HFC conversation and HFO, there's huge emphasis on reducing HFCs in Europe. And even HFOs, there's some very dramatic legislation that's just been voted through in the European Parliament. We're yet to see what the UK decide to do, but I've got a feeling it'll be to mirror exactly what Europe's done, if not potentially even a bit more stringent and stronger. So there's a twofold focus on exactly what we're doing at the moment, which is going to be an exciting growth curve for us over the next few years, hopefully.
Yeah, no, I believe it will be, because the more people I talk to globally, they keep talking about this reduction, phase down and phase out of these refrigerants that are there, high GWP refrigerants. And then I hear more and more about PFAs and TFAs and all this stuff. So we're going to see a huge shift, especially if regulations change. Like here in North America, they have an AIM that coming out. And that's like everything's has to be below 150 depending on what state. But I think if that comes out, I don't know if it matters what state or not, but it's kind of what's going on with the F-gas regulations. Like it's just, you got to have refrigerants super low GWP, and CO2 is one of those really low GWP refrigerants.
It certainly is. And there's no disadvantage to using it really, other than in really high temperatures. But obviously, as we've discussed on the previous podcast, there's technologies there that are helping it in higher ambience, and engineering practices that can really kind of make CO2 efficient in those higher ambience. But it's now scaling down. If you look at what Emerson are doing with the transcritical scroll compressor, that's getting down to about, sorry for my metric speak, but yeah, it's getting down to about 6, 7, 8 kilowatts is easily achievable, and lower with some of the other rotary compressors. So the technology was kind of designed around quite big numbers originally, but it is scaling down as well as it's scaling up. I mean, I was having conversations with some of our suppliers in Italy, and if you look at what bits we're doing now as well, the technology is scaling up massively, with 100-meter cube sweat volume compressors, 8 cylinders, there's a lot happening at both ends of the scale with CO2 technology, and again with heat pumps as well.
Yeah, no, and I've been seeing that for years. I know Vilter as well released their high pressure screw compressor there, because like my friend Benoit says, like he doesn't want to see 47 compressors on a rack. You know what I mean? And that's why Bitzer's making bigger ones, Durin is making bigger ones, and then Vilter's coming out with these bigger ones, which makes sense. And we're going to see, which is great, we're consistently seeing the evolution of new products, bigger products, better products for CO2, because you've been doing this since 2006, 2007. There was nothing 15 years ago, and now there's a lot of opportunity and options, which really helps the industry. This helps reduce the price, the cost of equipment, because now dies are made, the lines are made for those compressors or those components, which is cheaper for the manufacturers to make them as well, because now they don't have to start from scratch, which is great for the industry, because you'll see options out there. Is it still difficult? For sure, sometimes, because there's a big demand, but it is something that we're going to consistently see grow. New products come out, bigger ones, like I said, and probably prices get more stabilized for the average person.
Yeah, and you see more competition where there were certain components in the industry that you could only buy from one manufacturer or two at the most. Now there's more and more manufacturers coming on stream, and that's introducing an element of competition. So there's definitely, although we've got obviously massive global inflation, which kind of clouds the picture, but generally, prices are, I think it's becoming more cost effective, because the market is getting more competitive and more suppliers have products. So it's win-win-win at the moment really for CO2.
Yeah, love it. I love it. So you make CO2 refrigeration systems, you make CO2 heat pumps. Where is, and this is a question for you, what is the hottest location your heat pumps have run in? So what was the hottest temperature so far that you have installed heat pumps out there?
Well, probably not that hot in the UK, but I think the challenge is really at the other end of the scale. How cold can you go? That's probably a more a more pertinent question, because generally CO2 compressors or the transcritical versions kind of run out of steam at about -18 degrees centigrade. So, you can't really, go much lower than that without going to a two-stage machine, and you've got to really start watching discharge temperatures on single stage. So really -18 is the absolute lowest limit that you can probably get to on single stage. So say that's a -10 to -12 ambient degrees in degrees Celsius. So yeah, I think it's there are, there's ways around that, but ultimately the higher temperatures, there's just no problem, because you can evaporate up to +15 and beyond, and there's various things you can do if the temperature gets a bit higher on the evaporator side. So I think the main question is how low can you go, rather than now how can you go.
That's interesting the way you say that. So you get the -10 Celsius ambient or -14 Fahrenheit. It doesn't really matter. You see there's a bigger challenge with that, because over the years I've always heard about the big challenges is heat. We can't get CO2 equipment in warm ambient places, and then all of a sudden we have these warm ambient strategies now: parallel compression, adiabatic cooling, ejectors. But you're saying that the colder climates, there's a big challenge that they're facing with designing equipment.
Yeah, because obviously trying to create heat with a heat pump, not the other way around. So it's kind of the opposite. We're trying to do the opposite with our CO2 plants and equipment. So the opposite applies in kind of the temperature that it's running in. So everything flips over, if you get what I mean.
Yeah.
So that's the challenge, is making it work in really low ambience. And really, it's our transcritical heat pumps are parallel compression as well, depending on the temperature of the return heating water. It's a very a lot of heat pump technologies out there, whether it's that use condensing, whether it's HFC, HFO, hydrocarbon, ammonia, all those refrigerants condense, and they give up their heat at constant temperature. Now, a transcritical CO2 heat pump gives up its heat, almost sensibly rather than latently, in the transcritical phase. So it's a very different type of heat pump. It works very differently. And I suppose to kind of really boil it down is that we can supply very hot water quite efficiently. So we can get up to, say, 85 degrees, even higher centigrade water flow quite efficiently, with one very strong caveat, is that the return temperature is quite low. We need a much lower return temperature with the CO2 heat pump. And can get up to 35, 40, even beyond 40 degrees Celsius on the return. And that just starts to eat into the efficiency, and we've got to adapt system design for higher temperatures, for high returns into the 40s, using parallel compression and ejectors. So a lot of the componentry is exactly the same. That you would look at one of our CO2 heat pumps and one of our CO2 industrial packs, and you'd struggle to tell the difference. There are some differences, but fundamentally it's a lot of the same equipment that we use and same supply chain, but the technology of CO2 heat pumps is very different from normal heat pumps. A bit like it's very different from a refrigeration system. There's some pros and cons to CO2 heat pumps. We like to look at the positives, and one of those is very hot water. I mean, there is no better heat pump technology for heating cold water, for hot water, for hot tap water, for showers, baths, whatever it is, for wash down cycles in factories. If you need water over 65 degrees Celsius, or even 60 to 90 really. There is no more efficient technology than heating hot water. If it's coming in out of the ground through your water main at say 5 to 15 degrees Celsius, there is no more efficient technology than a CO2 heat pump to heat that water, as long as everything's designed correctly on the water side and on the heat pump side. So yeah, it's very, very similar technology to refrigeration, but it works in reverse.
Yeah. No, exactly. And this is what I heard lots. Like you can take any heat pump with any HFC or synthetic refrigerant out there, it just will not get as hot as CO2 can make that water. So, like you said, you got to make sure when you're selecting this, you got to have the right design, the right application, because you might be over designing, or because if you don't need to get 185 degree F or 85 C, then and you only need 50 or 60 C, that's different than when you're going to a big CO2. But I'm assuming at some point, as you see here, regulations is going that direction. At this point, what it looks like. Let's talk a little bit about that return. Like you're saying, one of the struggles is getting to that return to say 35 to 40. If you have that return is good. What are some of the things that you either have to have your team, your technicians, or your customers look out for when that return's starting to get out of range? What are some of the things they have to look at?
Ultimately, I mean, it does get quite technical, but it puts more and more load on the parallel compressor, because it's effectively, when that return temperature is, say, coming back at 40 degrees, that's like having a 40 degrees centigrade ambient temperature. It's exactly the same. The system's fighting quite a high ambient temperature effectively. It's almost a mirror technically of the challenges to the system. So if it's 40 degrees centigrade, if it was a refrigeration system, that's quite a challenging temperature for CO2. It isn't its limit, but that's where things get quite challenging. So it's exactly the same. But there's one big caveat with all of this, is that every heat pump, it doesn't matter what technology it is, it could be an ammonia heat pump, a hydrocarbon heat pump, every heat pump works more efficiently with lower water temperatures. So system designers, the consultants that build, that design the mechanical and heating systems and cooling systems in any building, they need to start designing for much lower water temperatures for their heating systems. That doesn't matter which what type of heat pump you're running with. It's about reducing that temperature as far as you can, and that's done by increasing the surface area of the heat emitter. So whether it's underfloor heating, well, underfloor heating is perfect because you don't need very warm temperatures. But say everything else, it is increasing the surface area of the radiators, increasing the coil sizes in their handling units, because everybody's used to heating water with gas. And gas can very efficiently heat water to 100, to boiling point quite easily and beyond, for heating steam. So everybody's got used to this gas technology, which is incredibly mature technology, and they've got used to engineering the water systems for it. For the whole world of heat pumps, water systems are going to have to be engineered a lot differently to create an efficient heat pump. And that is basically reducing the flow temperature as far as you can, and that's done by increasing surface area. And that, if that methodology will make every heat pump more energy efficient and work smoother and more energy efficiently. CO2 is no different. The lower the water temperature, the better. What CO2 can do is, if you do get the heat emitters right and you can get that return down as low as you can, then the efficiency gets higher and higher and higher. So the lower the return temperature, the higher the efficiency of the heat pump. yeah, what we've done on one project that we won an award for is the designers of the heating system have put temperature limiting valves on the exit of all the heat emitters. So whether they're or on the outlet of the heat emitters, so whether it's an air handling unit or a radiator, it's got a little deforst valve that only lets the water out when it reduces to a certain temperature, and that's worked very well indeed. It's been a challenging project, and we've all learned a huge amount on it, but ultimately we're getting water temperatures back that are perfect for CO2 heat pump, and it's worked very well, with a lot of learnings along the way. But it's working a treat now. So yeah, these are the things that we're considering in re-engineering heating systems to work well with heat pumps. It isn't just create a heat pump and everything will be fine. The water side and the heat pump need to work together, and the water side has to be tailored to work with a heat pump.
So you're saying, so on the water side, you got a valve on there, and it keeps the water in the heat the plate or the coil until you hit
Yeah,
a certain temperature, and then all of a sudden it'll start to flow again.
yeah. It doesn't pulse, but yeah, it really kind of makes the heat sit there and come out of the radiator or the heat emitter, and then it lets it out. I mean, obviously the radiator isn't going to be as hot to touch, but that's just the way heat pumps are going to work. It's about increasing that surface area and then reducing. So this scheme that we did was also reducing the amount of heat you actually need. So all the windows were changed in the building for double glazing, and all the insulation was improved in the roof. And so it's the decarbonisation of heat is also reducing the amount of heat you need and the grade of heat you need. It's not just fit a heat pump and everything will be fine.
Yeah.
It's many layers to it to get it efficient and effective and a working system. And so part of our job is trying to educate system heating engineers to these traits of heat pumps. And then there's particular traits around CO2 heat pumps. So yeah, it's a whole new world for our industry, but one that we have a huge almost obligation, or it creates a massive opportunity for our industry to contribute into to the heating industry and the decarbonisation of heat per se.
Yeah, I like that what you said there, because it's not just you just replace the equipment and all of a sudden everything's butterflies and rainbows. There's a lot of work that's involved in this stuff when you're doing electrification, you're doing upgrades, you're trying to help your customer have the most efficient system. There's a lot to think about. So if someone just comes in and says, "Okay, we can replace your boilers for heat pumps," it's just not the case because, and I've heard this before, people trying to just sell a piece of equipment to sell equipment. No, you need to work with your customer. Just like Daniel said, it's important to understand, how's the envelope of the building. Is that why they were using so much, burning so much natural gas? Because the building itself was an issue. Because you're right, it is a big challenge that we have faced ahead of us, but it's a good challenge is that we can work together to really understand this heat pump model, because a lot of people don't understand, even me, like I'm still learning it, because I came from the gas world. I still even have a central air in my house, right? So I got natural gas coming in, I just turn it on and she can heat up real warm real quick, but that's just not the case with heat pumps. And this is what consumers or customers are going to have to understand too, from residential all the way up to industrial, I'm assuming.
Absolutely, and it's a lot easier on a new building. A brand new build, it can be designed quite easily to work with a heat pump. It's the retrofitting, going back to old buildings where, and I think CO2 has a big part to play in that, because it's a sustainable refrigerant, but we can supply hot water temperatures, 70 degrees centigrade plus, into the 80s. So it's probably a technology that can play a big part in retrofitting, as long as the building owner and the engineer understand that it isn't just a case of fitting a heat pump and off you go. It's far from that. It's got many layers to it, in building fabric, as we've discussed, water temperatures and heat exchangers, but then the control systems. What we found is a lot of the control industry, the building management control systems, those guys don't generally understand how to control a heat pump. So we've had to work very closely with building management systems, the likes of the company. We have a company called Trend here, Trend Controls. Have you heard of Trend Controls? Siemens Controls. All the building management controls companies need educating to it as well. But the prize is big. In terms of the decarbonisation of heat, it is going to have a massive impact. We're talking to several companies now where they just want to shut the gas main off. They don't want to be burning gas. I've had that conversation 3 times this week.
Wow.
Big 3-4 inch gas mains, just want to cap it off. And it creates a challenge for us, but it's also a great opportunity for our industry.
Yeah. No, and I like that. So it's not like they can just cap it off. One of the things that you said there, that you need to teach, or like lots of people need to learn about heat pumps, going from boiler systems that are heating water now at this point. One of the things, when you go from, say, a boiler water heat pump to like a CO2 heat pump, the flow, because you said it about it earlier, would the flow change? Would you have to have higher flow rates for a CO2 heat pump, like moving that fluid, than a boiler?
Ultimately, we've got to heat water that's coming out of the ground. If it's for hot water, we've got to heat that from, say, 5 degrees in the winter, all the way up to 60 to 70 degrees centigrade. So flow rate is very low, to do that. Obviously, the heat pump has to grow if you want to increase that flow rate. But the most important part of a CO2 heat pump for heating hot water is the water side, and understanding that you've got to get stratification in the tank. So the hot water's at the top, the cold water's at the bottom. And that's a very key thing for making and understanding how to store a lot of hot water in different buffers. And the systems can get quite complicated, but what you're trying to do is create very hot water and then not reheat that water. It hopefully stays hot, and then the cold water comes into out of the main into the bottom of the tank, and the heat pump draws off that. So the heat pump's always seeing the coldest water it can. But obviously we've got to have double wall segregation, so there's different heat exchangers in the system to do that. But what we've found is if you get the stratification right, is that it can be a very stratification works very well. We've seen temperatures at 70 degrees, and then maybe a foot down it's 35 degrees. You can have really significant, and it's that stratification for heating hot water that's very, very important. It's tricky to do. It is tricky to do, but that's something that that's what makes a good CO2 hot water heater. I mean, the Japanese have been doing it for a long time, obviously in Japan, with what they call the EcoCute system. So most houses in Japan have hot water heated with a CO2 heat pump. So we're not talking about a new technology here. In fact, it's in certain quarters of the world, it's quite a mature technology. So yeah, there's a lot to learn, but if our industry can't do it, then decarbonisation heat isn't going to happen. We've got to adapt as an industry to meet this challenge, because the decarbonisation heat depends on our industry. It really does.
Yeah, And it's I like what you said there too, because a lot of people ask me, well, when will we ever see CO2 in residential applications? I'm like, back in 2000, that's when probably was the first time the Eco Cube. I think it was 2001. I don't even know. It might even been before that. And I'm just like, it's been in residential applications for a long time, and it's just nobody knows about. We don't talk about it, and it's not a new technology. And we're going to see more and more of it. And even here in Canada, there was installations like over a decade ago with residential. They were trying residential CO2 water heaters, right? So it's
Yeah.
something that's been around for a long time, and we're going to see it in more and more applications. But it's good. I like that what you said, the stratification. I guess that would be a strategy or a design or both.
Oh, it's definitely, well, it's the strategy. You've got to say, right, we're going to stratify this water tank, and then a lot of it is design, and getting the design right, the flow rates right. Um, we've seen it done badly, and we know how to do it well now. So it does make a huge difference.
So could you
But
give
it's
a
very important with particularly with a CO2 heat pump.
sorry, could you give a couple of tips what not to do for people like when they're figuring out for stratification, just to help some people out there where it like if I was a technician running into an issue or a designer trying to figure out the status, what would be one or two things that you want to stay away from trying to figure out this
Yeah,
stratification?
high flow rates, and really you've just got to stay away from turbulence in the buffer vessel.
Mm.
You've got to just keep all the pipes sized, nice and generously, so you've not got any turbulence in the water flows. And you've just got to go. Going slow is the wrong way to phrase it, because you can do some big duties, with these systems. I mean, we're doing 150 kilowatt water heating systems. Well,
Wow.
100 to, really, you can go as big as you want, but ultimately it's about keeping the velocities quite low in the pipe work and the tank, and configuring the tank, obviously, so that it's always pulling the cold water from the bottom. So yeah, it's just about control as well, flow rates. There's certain things that we're doing so that when the heat pump starts up, you don't want to put a load of cold water in the top of a hot tank. So we're diverting the water on startup, and there's quite a bit to it, but ultimately, it's not rocket science either. It's just learnings from experience, really.
And I like that too because it's all about learning, growing, getting a little bit better each day, and figuring out. I think the best thing is like you guys are such experts by trying it and doing it, and oh, this didn't work. Let's try this, and okay, let's try this. Oh, that seems to work better. Let's try this a little bit more, and just fine tuning and getting better and get better and spending time at it. And I think you're right. Because that example you said earlier, you got 70 Celsius water, and then a foot lower, you got 35-degree water. If you have a lot of turbulence, that's going to mix up a lot more, and
Exactly.
and then
It's
you're
about
gonna.
keeping everything very steady.
Yeah, that's cool. I'm excited to learn more and more about these because I really believe there's a huge influx, especially coming into North America. I've talked to so many contractors like, okay, and we're getting these CO2 heat pumps. If we like it or not, we got to start learning it. Trevor, can you help teach us? So, and this is why I'm talking with you to learn a little bit from you, so I can share it with other people.
Yeah, yeah. But yeah, it's there's two applications. We've actually done an application where we can swing the heat pump between heating space heating and heating hot water. So 1 minute it can be running as a hot water heater for tap water, um, and the next minute it's heating a district main for a campus.
Wow.
So with different water temperatures. So when we're obviously heating for hot water, we're supplying water at 70-75 degrees, and then the next minute we'll be supplying water at 55 degrees Celsius for the heating circuit. But that again is controlled. So if it's very cold outside in the middle of winter, it's just compensated. We might be supplying 65 to 70 degrees into the heatings to heat the buildings. But in the middle of summer, or I'm sorry, in spring where there's not much heat required, we're compensating right down to 55 just to save energy. So there's all these layers of, we've got, I know last time we spoke, Trevor, we talked about glycol defrost, but that's incredibly important in the middle of winter, is defrosting heat pumps, and minimizing the defrost and making sure defrost is energy efficient. So we're using glycol defrost systems to defrost our heat pumps.
So yeah, no, I remember that conversation very well. So because I've never even thought about doing glycol defrost. One thing, so you said that it could cost more money. Would that be from running the defrost too long, heating up the glycol too much? What were some examples of where defrosting could cost you more money?
We're all, we've obviously, as an industry, got, if we're fitting heat pumps to decarbonize, to electrify heat, to decarbonize heat, to be energy efficient, to use as little energy as possible. It's a bit like your electric car. They're rated on how many miles they can do per kilowatt hour. A heat pump's not much different. How many kilowatts of heat can you get out of it for a kilowatt of energy? And the more energy you put into defrost, you've got to count that as used energy. It's part of your running costs and running efficiency. So we won't use electric defrost on our heat pumps. It's expensive, and it's quite it creates quite a maintenance headache as well if the heaters go down. And there's some of the projects we're doing are big, the megawatt, 1 megawatt heat pumps, or certainly 750 kilowatt heat pumps. That takes a lot of defrost energy, and to generate that with electric would be totally against my rule book, to be honest with you.
That's
so
fair.
we there's two options. You can either go reverse cycle, which is very complicated, needs a lot of valves. It's a bit like a hot gas defrost, Trevor, that you've done a few videos about. It obviously works, and it's a good concept, but on the scale, when you start getting up to industrial kind of duties, big numbers, it becomes quite complicated getting liquid back, and the valves are expensive, and servicing it going forward. Service technicians. It's getting them trained up and understanding hot gas defrost is always tricky, and so we just go for the simplicity of a glycol defrost at the moment, and it is so simple. It's just when you want a defrost, just run a pump and pump some warm glycol through it. So and the glycol actually is pulling out of the return. So when I said the return water's like 42 degrees, during defrost it might come in at 42 or 40 and leave at 36. So your heat pump on a defrost cycle is using heat that it is already generated to melt the ice in the coils. So it's a very good system, and it works very, very well.
So when you do that, so you're saying that comes from the suction side when you're doing the defrost?
No, it comes actually from the water that you've heated, or you've sent the hot water out at 70 degrees.
Yeah.
You bring water back at, say, 40 degrees, and then we put a heat exchanger to the glycol. So when the glycol pump's running, it's actually pulling heat out of the return. So the heat pump will actually see 36 degrees, if you get what I mean.
Yeah, totally do. Thanks for re-explaining that to me. Return. Yeah, and that makes so much sense. This is what I'm learning to talk about more. We're moving energy, we're moving heat, which more of us need to talk that way, because it gives me a better picture, because we are transferring things in different locations. In our refrigeration systems, we're just wasting the heat to the air. But now with newer systems, we are starting to become a bit smarter and reusing that heat, like in heat pumps and systems with heat recovery and heat reclaim, because I think it's really important to reuse as much energy of that one system as possible.
Yeah, and
With
it's not just energy; it's compressors. So we're looking at food when you're looking at a food factory application, and you're running you're chilling a food factory. Um, in the winter, you've got a lot of compressors that are sat there doing nothing because there's not much refrigeration needed. So in the summer, they're really, they're running flat out. All the compressors are running. There's no spare capacity. But in the winter, you've got at least half your compressors, if not two-thirds of them, sat there doing nothing. So our philosophy is, well, let's run those two-thirds of those compressors as a heat pump, and then you're effectively making your compressor assets work for you all year round.
Yeah, that makes so much sense too. Because if you want to save as the most energy possible, you just shut everything off. Don't run anything, right?
Yeah,
But then you don't have
yeah,
a system at all. So, but if you want to, yeah, best systems, everything's running as much as possible, because that's all about design. At the end of the day, design properly and effectively, you can get the most out of that. Because I think you're totally right. Just having a bunch of tens of thousands of dollars worth of equipment not running for half the years. I don't know if that's the best bang for your buck, but that's what we do at this point.
it's what we've done as an industry forever.
Yeah.
But now we're looking at systems and saying, well, those compressors that would normally be switched off, let's run them as a heat pump and give the building back some heat, because often the heat that we can generate from refrigeration is in the winter is snapped up very quickly, and they're going, well, we want some more heat. That's not enough from heat recovery. We want more, so we can give them more by running the spare compressors as a heat pump. So that's the way food factories are going to work from now and in the future. That's where they're going to get the heat from. Is their refrigeration equipment is going to supply the heat that they need.
Yeah, and I was at a site with a good friend of mine from our NAG, Phil Walker, and that refrigeration system does just like you said. They does the medium temp, the low temp, air conditioning, and the heating of the system. So we're going to see more and more of that coming happening around the world. It does it all. So, and it's because of CO2. You can't, you wouldn't be able to just use any refrigerant to be able to do that, to my knowledge. So,
Yeah, I think I'd say you probably can use others. I mean, but it's not just food factories. It's supermarkets. Anybody that's got a need for heat and a refrigeration plant, then a new refrigeration plant should be designed so it can run half as a heat pump, half as a refrigeration plant, so that it can supply heat, whether it's a supermarket or any. We've our heat pumps, our CO2 heat pumps can provide simultaneous heating and cooling. So the cooling just comes from, rather than running the air source evaporators outside, we just run a plate heat exchanger. We can provide chilled water. So the chilled water is actually creating heat for the heating side. So it's just, this is what air conditioning companies have been doing for years. Mitsubishi, the VRF, and Panasonic, but it's taking that kind of philosophy and applying it into bigger scale refrigeration projects.
yeah, and what I really like is that there's just lots of change happening, and I really enjoy the change in our industry, where we're going to see more refrigeration technicians working on heat pumps and more heat pump guys working on refrigeration systems, just to broaden our knowledge. And I think that's going to really help technicians become better at what they do. Is it going to be challenging at first? 100%. For the last 20 years, I've been hearing there's a challenge, there's a knowledge gap, there's a skill issue, and all this stuff. Sure, there is, but there's a lot of people out there that want to learn this stuff and get better and grow. And when you can work on these different systems, especially on the CO2 side, it's going to just make your troubleshooting, your skill level a lot better. And I've been seeing CO2 bring in different parts of the industry, like I said, refrigeration, HVAC. And now when we talk about CO2 equipment, you have to have a little bit more knowledge in just the basic stuff, which is good. Safety side, things like that, which we did need to know with the HFC, but we did it for so long in the synthetics, people start just, maybe
Yeah.
forget a little
Well,
bit.
the young people that are going to come into our industry from like now or even 2, 3 years ago, and in the future, the people that come into our industry will just think it's normal. It's
Yeah.
just, they they might hear stories of old systems, but the
Yeah.
new systems, heat pump systems, natural refrigerants, and high pressure systems, and all these conversation points, which you're right, they're very new and it's great and exciting for our industry. But to the people that are just coming in now, it's just going to be the norm for them. And again, I know we said this last time, it's a great industry to be getting into because there's a lot of conversations in the world around AI, and it's going to be a long time before AI can fix a CO2 plant. We're going to be needed as an industry. We're going to be leaned on very heavily, and our careers aren't going to be replaced quickly at all.
No,
So,
not even a little bit. Not even a little bit.
yeah.
So that's something that we need to be proud of for our industry for sure, because we'll be working a lot more now than ever before if we wanted to. And it's just all about learning, and it's a great time to be in refrigeration. And I'm excited. I'm really excited, and I'm excited for what you're doing, because even in the last few years since we knew each other, I see your business growing, your team's growing. You guys are just, you keep pushing the boundaries, which I love. Daniel, how can people get a hold of you if they want to learn about your heat pumps, your CO2 systems, to be the best contact for you?
Yeah, it's I'm on LinkedIn, Daniel Clark without an E. Email me at daniel at isentra.net. I'm sure you could put something out there, Trevor, with our contact details on. If anybody ever wants to pick the phone up, or WhatsApp me, I'm sure you pass my number on. But yeah, we're open to conversations. We've got a lot of exciting things happening within our company. We've got new premises on the way, big new factory, and it's CO2 is really starting to happen at both ends. We're seeing industrial refrigeration moving to CO2 quite heavily now, and then obviously the heat pump side of things. So yeah, it's going to be a bit of a roller coaster ride, hopefully, for the next few years. But we're perfectly open to any conversations. I was talking to you, put me in touch with one of your Australian friends. We had a really good conversation, a few weeks ago, and I'm perfectly, open to talking to anybody.
I really appreciate it, Daniel. Thank you so much for sharing your knowledge. I will definitely have you on here again because I want to pick your brain. You got so much CO2 knowledge to share. I appreciate it. I want to thank everybody for taking the time, for listening. I really appreciate that. Head to the Refrigeration Mentor Instagram page or Facebook or LinkedIn to learn more. Please share this with others because this knowledge here, we want to get it out. We want more people to learn about CO2 heat pumps, get into contact with manufacturers like Isentra, just to build that knowledge, to build awareness. Daniel, thank you so much, and I'll see you all at the next CO2 Mondays. Thank you.
Yeah, cheers, Trevor. Bye.